I'll hand it over to Dr. Dinuka to conduct the keynote speak, but I'll just do a small background on Dr. Dinuka. So he'll talk more about his background, but I'd like to introduce his main area of expertise. So he's a staff IC designer at Broadcom in Sydney, Australia. He has done a PhD in wireless communication at the University of Melbourne uh, uh, from 2011 to 15, I believe. And then he's also a past alumni of the University of Morotua, the electronics department. And yeah, I would like to warmly welcome him and thank him for accepting our invitation. Um, yeah, all over to you, Dr. Tinuka.
Thanks, Hitman. Can you guys hear me clearly?
Yeah, we can hear you clearly.
Good. So let me. Thanks, Kitmin, for the nice introduction, and good morning, everyone. It's a pleasure to be here to share a little of what I have learned through my academic journey, as well as my experience as an IC design engineer in the semiconductor industry. My aim today is to give you a practical view of how SoC design works in the real world, using examples from modern wireless systems. I hope this talk gives you a clear picture of the field and shows why it is such an exciting area, and perhaps even inspire some of you to explore it further. Let's start. As Kipin explained, my background combines both academia and industry. And I completed my undergrad studies at ENTC in 2010 and my PhD in energy efficient wireless systems at University of Melbourne in 2016. Since 2017, I've been working as an IC design engineer at Broadcom, mainly on Wi-Fi SoC products. My work has involved areas such as system design and simulation, emulations, verifications, silicon bring up, and various tool developments. So this presentation is shaped by the hands-on product development experience. For anyone who is not familiar with Broadcom, I'll give a brief introduction. It is one of the largest semiconductor companies in the world, and currently I think it's like number 6th or 7th in the entire world in terms of the market cap. Its semiconductor business spans across areas such as AI XPU, networking, wireless, broadband, and storage. Just a quick disclaimer before I start. This talk reflects my personal views only and does not represent any view from Broadcom or its affiliates. And this presentation uses only public information. And the Wi-Fi case study is just a general educational example, not the exact flow of any specific product. So let's start with a simple question. What is a system on a chip, or SoC? When we use a smartphone, we usually think about the apps or the software. But underneath that, the software is a remarkable amount of hardware integration. And at the heart of most modern devices is a system on a chip, or SoC. And that brings many of the core functions of a system into a single integrated circuit. That does not mean the whole phone is one chip. In practice, smartphone usually includes multiple chips or companion SoCs for functions such as main processing, cellular connectivity, Wi-Fi, and power management. The main SoC, the central computing engine, integrates functions like CPU, GPU, or neural processing units. And this type of level of integration, it did not happen overnight. The chart on the right-hand side shows how transistor counts has grown over time. In line with the long-term trend, we often call as Moore's law, which doubles the technology every 2 years. And from Intel's 4004 in 1971 here to current Intel's 4004, which had about 2,000 transistors, to modern processors with tens of billions of transistors. And that growth has made it possible to move from simple processors to highly integrated SoCs that now power everything from a smartphone to GPUs, XPUs, and AI accelerators. So the key idea of this slide is simple. The SoC is a product of decades of progress in semiconductor technology, and Moore's law is one of the central reasons that this extraordinary integration became possible. Before we dive into the technical journey, let's first briefly look at the economic scale of this field. The semiconductor industry was already worth of 775 billion in 2024, and it showed how large and strategically important this sector has become. Looking ahead, traditional industry forecasts show about 1 trillion by 2030, and recent analysis reports from McKinsey using a broader market framework and a very strong AI demand shows that this number could be increased up to 1.6 trillion by 2030. And logic and SoC devices form the largest product segment, which makes sense because SoCs are now embedded in almost every major computing platform, from a smartphone to AI data centers. In other words, SoC engineering sits right at the center of one of the world's most important industries. Now that we have seen why semiconductors matter economically, let's look at one case study that shows why SoC design is so technically rich. For this talk, I've chosen Wi-Fi 7 because Wi-Fi 7 SoC brings together almost every major discipline in modern chip design within a single product. As you can see, it combines RF and analog design, high-speed baseband processing, digital logic, and packaging and post-silicon validation. Features like 320 megahertz channels, 4096 COM, and multi-link operation push both the radio and the digital architecture much harder than previous generations. And unlike a purely theoretical example, Wi-Fi 7 product must also pass real certifications and real production testing before it can ship. So this particular case study gives us a practical and modern way to walk through their full product design cycle. This slide is the roadmap for Wi-Fi case study. It shows the full journey from modern SoC from the first specification to the all the way to the shipping product. I'll use this as the map for the next few slides, where we zoom into each major stage on more detail. First, we have the design phase. This begins with the system definition or system specification, and then moves into a system architecture, then RTL coding, functional verification, and this is where the product is defined logically and verified before anything is physically built. Next comes the physical design. This includes DFT and synthesis, which I will explain a couple of minutes later. Flow planning, placement, clock tree synthesis, routing, sign-off, and tape-out. This is where the logic design is converted into a physical layout and prepared for manufacturing. Finally, we move into manufacturing and productization. This covers foundry fabrication, packaging, bring-up, certification, and mass production run. This is where the design becomes a real valid product. So from the first specification to an actual silicon chip, this SoC journey takes a long multidisciplinary, and it often takes multiple years to the final production. Now let's focus on phase one, the design phase. This is where the product is defined logically before anything is physically built. The first part is system specification and architecture design. Here, the requirements come from IEEE standard, the applications, the customer needs, and the expected performance and features. For example, Wi-Fi 7 supports up to 320 megahertz bandwidth and higher order modulation schemes. So the transmitter, receiver, memory, and processing architecture all need to be designed to support these specs utilizing the optimal performance. At this stage, the system is split into major blocks such as PHY, MAC, security, and other interfaces. Many features are developed at this stage to optimize the resources and to achieve higher performances with higher reliability. We use simulation at this stage to obtain performance across many different scenarios. The next major part is RTL design and verification. This is where the system architecture is turned into hardware code for the major blocks. In many real projects, this is also where the large part of the time is allocated. The RTL is written in languages such as System Verilog and VHDL, and then it is verified using a large number of simulation test benches. Hundreds of thousands of directed and random tests are used to catch bugs and corner cases, which then increase the accuracy of the design. We also use emulation platforms and FPGA for the before tape out to validate more realistic system behavior, and EDA tools from vendors like Cadence, Synopsys, Siemens, and also open source tools like Verilator could also be used for these testing and verifications. One important aspect of these functions could be overlapping in time, and this is an iterative process. So the key message of this phase is simple. Mistakes are cheapest to find on a screen before they become expensive silicon problem. In the second phase, physical design, it's become a manufacturable physical layout. The first step is design for test or DFT, synthesis and floor planning. We add test features so that the chip can be checked and tested after manufacturing. We convert the RTL into gate level netlist and also plan how the major blocks will sit on die, including keeping sensitive RF and analog components away from noisy digital logics. Next comes the placement, CTS, and routing. Placement decides where cells and blocks sit physically on the chip. In CTS or clock tree synthesis, it builds the clocking network and it synchronizes the chip and has a major impact on timing quality and performance. Routing then creates the metal connections between everything. These steps are again iterative. The layout is refined again and again to meet timing, power, area, and manufacturability targets. Finally, we reach the sign-off and tape-out phase. Here, the design is checked across key operating corners. We also use extracted parasitics. So the analysis includes the real resistance and capacitance of the routed wires, unlike the ideal components that we learn in the university. That makes the results much closer to silicon, real silicon. Final checks then confirm that the layout is manufacturable and robust for timing, signal integrity, power, and reliability checks. So this is the major gate before GDS2 release. After that, fixes become more expensive. In the third phase, it begins when the design leaves the digital world and enters the manufacturing world. Once the GDSI with the GDS2 database is released to the foundry, the focus shifts from design completion to the building, testing, and qualifying real products. The first step is the foundry fabrication. This is where the chip is physically manufactured layer by layer on a silicon wafer. The process involves a very large number of fabrication steps and takes several months. At this stage, yield is critical. Because even small defect levels could significantly affect the how many working chips could come from each wafer. Here, the yield means the fraction of manufactured chips that come out of working correctly, out from a wafer that works correctly. After fabrication, the chip exits as a bare die, which simply the small piece of silicon containing the circuit, as you can see in this diagram. That die is then assembled into an IC package, which protects it, help remove the heat, and also provide electrical connection to the board. In many wireless products, the package chip is then integrated into a SiP module, means system in package, together with the other components such as power amplifiers and passive parts and connecting sockets like antennas. This makes the final solution smaller, easier to integrate, but it adds also add complexity in packaging and production tests. The next step is bring up and post silicon validation. This is where the final real chips are powered on in the lab. The bring up team first checks that the device boots correctly, and after that they calibrates the RF sections, measures the actual throughput and performance on hardware. Any issues found at this stage are debugged on silicon, and if necessary, a small late fixes may still be applied before the release. Finally, the product must pass the regulatory certifications before it can be shipped. So the key message of this phase is that a successful SoC is not finished at tape out. It still has to survive manufacturing, packaging, validation, and certification before the product ramp up. So far, we have looked at the SoC journey from design through productization. The next question is, how is the industry evolving beyond the traditional single dice or monolithic chips? One of the most important answers today is chiplets and advanced packaging. Let's briefly look at how the industry is moving from single dice to multi-die systems connected within one package. So starting on this left side diagram, this is the traditional monolithic die approach. All major functions such as CPU, GPU, input-output, and memory are built onto one large piece of silicon, usually on a single process node, same node like 5 nanometer or 7 nanometer. That is elegant in concept, but as chips becomes larger, the manufacturing gets harder and more expensive, also sensitive to more defects. A defect anywhere on that large die can reduce the yield significantly. So on the right-hand side, you can see a chiplet architecture approach. Instead of putting everything on one die, the system is split into smaller dies or chiplets. Compute can use a more advanced node, while input-output can stay on a more mature and low-cost node. These chiplets are then connected together inside one package. The advantage is more flexibility, better reuse across different products, and often better manufacturing economics when you take compared with the large monolithic die. Now, in the bottom left, you can see 2.5D packaging. Here, the different dies are placed side by side on a silicon interposer. A silicon interposer is a passive silicon layer that provides high dense wiring between the dies. This is especially useful for pairing logic with memory, which is why 2.5D is common in AI accelerators. And now we have 3D packaging. This means dies are stacked vertically on top of each other instead of sitting side by side. And that shortens the interconnections, improves the bandwidth, and increases the integration density. This is especially valuable when both performance and energy efficiency matters. But the downside of this architecture is that the thermal management becomes more difficult. So managing heat could be a bit more difficult. And the bottom right-hand side, you can see hybrid integration, or sometimes called 3.5D. And this is a combination of the previous two packaging, 2.5D and 3. And some dies sits laterally besides each other, while the others are stacked vertically in the same package. So this is about building a very large, highly integrated systems by combining the strengths of both 2.5D and 3D together. Tying all this is UCIe, or Universal Chiplet Interconnect Express, and it brings it makes the multi-vendor chiplet ecosystems possible. One trend before we wrap up, this trend is the combination of open instruction sets and domain-specific silicon. RISC-V is an open royalty-free instruction set architecture maintained by RISC-V International. And unlike a proprietary ISA, anyone can implement, extend, or commercialize RISC-V core without paying a licensing fee. So that opens a path to academics and also the products like custom accelerators and domain-specific extensions. The second piece is the domain-specific architecture, and a processor microarchitecture tuned for like one workload, such as matrix multiplication, signal processing, or cryptography. It can deliver like 10 to 100 times higher energy efficiency compared to a general purpose CPU of that workload. What's the cost? The cost is the flexibility. A DSA is fast on its target, but comparatively poor if you use it to do a different task. And AI accelerators are the clearest published example, reaching hundreds of tera operations per second. These two ideas combine very well. A small open RISC-V core as the control processor with a custom domain-specific data path around it. And that pattern is already appearing on edge AI devices, radio DSP, and secure elements. For students, the barrier to propose a novel hardware is lower than it has been in decades. And I think this workshop also follows the same type of architecture. Let me end my talk with a practical message, especially for the students. Sri Lanka already has a strong ICT export sector and a growing base of electronic engineering graduates. So compared to 10 or 15 years back, now there are more established hardware design companies and even some EDA presence as well. So entering semiconductor work from Sri Lanka is less about the location and more about whether you can show technical ability. The good news is that the tools are much more accessible now with tools like OpenRoad, Verilator, CocoDB, and open PDKs like Sky 130. It is possible to learn professional style digital design flow at very low cost. Even an FPGA board is enough for a credible first end-to-end project. And in fact, I think some of the students who are participating today's workshop have already taken part in such IC design competitions and shown that they can complete real design work towards tape-outs. If I had to propose a path, I would put it in these four steps. First, build a strong foundations in HDL, test benches, and full digital design flow. Second, create a hardware proof through FPGA projects with reproducible scripts in public repos. Third, publish a research paper or poster based on your designs, make it meaningful open source contribution. And finally, you could aim for global exposure through master's or PhD study like some of us here, and international internships or collaborations that could give you access to broader teams. So the main message in this slide is the path is possible from Sri Lanka. What matters most is the time, discipline, and the visible evidence that you could build something real. So this concludes my talk, and I'd like to thank Kitmin and Abba for conducting the workshop and giving me the opportunity to share my ideas. And I'd like to wish you all the best for the rest of the workshop and for your future endeavors. Thank you.